Hello everyone, welcome to the P1 program. This lecture is called P105. In this lecture, we are going to look at the kinematics and one-dimensional kinematics and the equations of motion and all that basics. Okay, so for that, I'm going to assume that I'm going to travel from say Kochi in Kerala to Delhi. Okay, and the distance between Kochi and Kerala, which is 1,000 kilometers, around 1,000 kilometers, and from Delhi I'll go to Saudi Arabia, which is around 2000 kilometers from Delhi, and from Saudi Arabia I'll go to Britain, which is around 2000 kilometers from Saudi Arabia, and then from there I'll go to Moscow, right? Moscow is around 3000 kilometers from Britain, right? If I do that, the total distance I've traveled, okay, the total distance I've traveled will be the sum of all these, which will be 4 plus 4, which is 8000 kilometers. So 8000 kilometers will be the total distance, and the time taken for me is, let's say, it's 5 days. Okay, if it's 5 days, then the speed with which I'm traveling is 8000 divided by 5, that is 1600 kilometers per day. Okay, that's the speed of my travel. Now if I look at something else, which is called the displacement. Okay, if I look at displacement, you'll find that the first displacement from origin, my origin point, the initial starting point is k, and from there the first displacement will be 1000, and the second displacement to Saudi Arabia, let's say it's be 500 kilometers, and the third displacement to Britain, right? The Britain and Moscow here. So to Britain, which is will be around 2000 kilometers, and from Britain to Moscow, from the origin, from Kochi to Moscow, that is around say 3000 kilometers. Okay, so the total displacement here is the initial and final point. That's the only thing that handles. Okay, so the final displacement is 3000 kilometers. So 3000 kilometers in 5 days, that is around 600 kilometers per day. Okay, that's the displacement with which I am traveling. Okay, that's called the displacement. That's a different thing. So distance is the speed, and the velocity. This is called the velocity. So displacement was 3000, and this is 600 is called the velocity. So speed and velocity, this is called the speed, and this is called the velocity, which are different things. Okay, which are different things. One depends upon direction and the other doesn't depend upon direction. One is a vector and the other one is a scalar. Now what I'm going to do is that I'm going to plot the displacement versus time graph. Okay, displacement versus time graph, I'm going to plot it now. So the first displacement is the from to Delhi, that's around 1000 kilometers, right? So that's 1000 kilometers. So the first displacement will be around 1000 kilometers, and from second displacement at say t1 and t2 and t4 and t3 and t4, this being the time axis and this being the position axis. So the first checkpoint we have at t1, I will be at Delhi, so it's 1000 kilometers away from my home in Kochi, Kerala, and the point I will be having is this. Okay, let it be that. At T2, I will be at Saudi Arabia, so it will be around 500 kilometers. So I will be around here. Okay, and at T3, I will be at Britain, which is around 2000 kilometers away from me. So I will be at here, that is 2000, around 2000. So this is 1500 and 2000. Now at the last checkpoint, which is at Moscow, I'll be around 3000 kilometers away from. Okay, 3000 at T4. So if I connect these graphs, if I connect these graphs from the origin, I'll get something like this. Okay, this is more called the displacement versus time plot. Okay, so this is called the displacement versus time plot. If you add up all these displacement, okay, you can get the final displacement. So final displacement is just 3000 kilometers, That's my final displacement from the origin, which is around here. Okay, so this is called the displacement versus time graph. Okay, now if I what I'm going to do next is called to introduce the concept of velocity. So velocity is just I've said about velocity numerically. Now if you look at it mathematically, you can see that velocity will be delta of x by delta of t, right? So it is just, if you look at the total velocity of this plot, it will be x final by x0, and this will be x0, this will be t0, and this will be t final. So velocity is just x final minus x initial by t final minus t initial, right? So here x final is 3000 and x initial is 0, so that's 3000 divided by t final is 5 days, so t final minus 0, which is 5, so that's 3000 by 5. That's how we get that factor. Okay, this velocity is called the average velocity. Okay, this is called the average velocity of traveling. Okay, now if we want to find out the instantaneous velocity at each point, okay, I'm going to redraw this graph just like that for convincing you that this was the plot. Now the plot looks something like this. Okay, so the average velocity means at some point in this graph you want to find out the instantaneous velocities, right? The instantaneous velocities at these points, right? This is what you're interested in. If that's what you're interested in, then you have to narrow down the whole point. You have to narrow down the whole point to a smaller value of t, delta t, and to a smaller value of delta x. So t is going to be small, so that means you can write down the equation of velocity as velocity of instantaneous velocity, which is equal to limit delta t tends to 0, which is small, delta t tends to small values, delta x by delta t, which is the instantaneous velocity at that point. So instantaneous velocity will look something like uh, x of t plus delta t, okay, at higher point, minus x of t by delta t, okay, with the delta t tends to 0. Okay, in that case, that's called the instantaneous velocity of the particle. This is the textbook definition of what is called the differentiation, right? So this is equal to dx by dt. So dx by dt is equal to the velocity. So instantaneous velocity. So instantaneous velocity is actually the slope of the curve at each point. So slope of the curve, if this is the point that you're interested, then the slope of the curve looks like this. If this is the point, the slope of the curve looks like that. If this is the point, the slope will look like that. Okay, a tangent line. That's how a slope would look like. So each of these slope adds up to, if you look at each of these individual slopes, right, these slopes adds up to a common resultant, and that is called the average velocity. So the average velocity looks like a resultant of each of these individual slopes. That's how average velocity will look like. Okay, so now what I'm going to do is that if you take that plot again, okay, if you take that plot again, it has two dips and one crest and one trough. Okay, one up point and one down point. So this is a common, if you want to generate an equation out of this plot, okay, 4 points. Now you filled in some smaller points to this graph, and you completed the graph, right? So you need to find out an equation for this graph. What you can do is that you can always write down an equation, a polynomial equation, which is the easiest thing that you can do. You can write down that x equals, you can write down like say t, or x equal to some constant times t, plus some constant d. Okay, this equation is the equation for a straight line, okay, with the starting point d and the slope c. Okay, that's the basic equation, right? Now if you write down the equation of a first order polynomial, this is a first order polynomial. Now if you write down second order polynomial, you can write down as a t square plus bt plus c. You can write it down like that. So it will look something like, depending upon this slope, it will look something like, say this. Okay, it will be a curve like that. It will have a slope, and you can find out the c will be, the initial starting point will be c, and it will have a curvature like that. Now if you go to higher order, which is a t cube plus b t square plus ct plus d, now this curve might have, okay, it's not necessarily, but might can have uh, a curvature like that. Okay, it can have a curvature like that, a dip and an up. Okay, that's how the polynomial can have. Now if you look at our primary curve, it had a crust and a trough. That means it's almost will be is a third order polynomial. So it must have a degree, a power of t raised to 3. It must have possess a power of 3. So our equation will generally must look like this. For this curve, this particular curve, it must look like that. So we can assume the values of a, b, c and d. Okay, c and d, and we can put down some values. And if we have a curve like this, right, you can numerically approximate. And if you have a source curve like this, okay, if it's the source curve, then you have to fit this curve, and for that you can introduce the polynomial, our approximate values of a and b and c, and then we can start from that polynomial. It might look something like this. Okay, and then we start to fit this curve. Okay, you can use Monte Carlo Markov chain or numerical other approximation. You can use it, do it by hand by changing the values of a, b, c and d. You can approximate this curve, and your final curve must look something that is fitting to the actual curve. The closest to that curve will give you the exact equation. You can do this numerically. Okay, that's a different field of study itself. Okay, so you can try that. You can try to do fit a curve, take a curve, some points, and then try to fit a polynomial equation into that. The only thing that you need to remember is that if you have a single variable like x to the have the power of x, it will be a straight line. If you have x square, it will look like this or look like that. If you have x cube, then it will look like this. Okay, if you have x raised to 4, it can look like that. Okay, so the curvature will increase with the power of polynomial. Introducing more polynomial means you are adding more features to the curve. Okay, so that's the only thing you need to remember. Okay, now getting back to our plot was something that looked like this. From the origin, it was starting from the origin, and it went like that. Okay, so this plot can have the equation of, let's say, x must be equal to, or x must be equal to some a t square plus, or a t cube plus b t square plus ct plus d. Okay, so that's the basic equation it can have in our plot. So the velocity will be dx by dt, the average velocity for the whole thing. In a ambiguous way, you can write it down like the derivative. So it will be 3at square plus 2bt plus c. Okay, that will be the time derivative of the equation. Now if you consider an equation of the second power order, okay, second order. So let's do an approximation like that. Now if you have a curve like this is representing your velocity, and the displacement versus time graph. Okay, let this be your time graph. So this has one dip, that means it will look something like x must be equal to some 3a t square plus 3bt plus c, right? So that's how you look at this curve, and the c is here, the constant, and the slope can be found out for that curve, and you can find out that dx by dt will look like 6a t plus 3b, right? So this has one variable t, so it will be a straight line. So the slope of that line is 6a and the starting point is 3b, so it will be around somewhere down below where 3b is here. This is 3b, and it will be a straight line that like that. So that will be our slope of the curve of this displacement versus time graph, and that slope is called the velocity graph. Okay, that slope is called the velocity graph. Now velocity versus time graph, if you look at the velocity versus time graph with 3b here, the each point represents a different velocity. Okay, this is a different velocity for your particle. If you say this is 100 meter per second, this is 110 meter per second, and 120 meters per second, then you can say that at t1, t2 and t3 you are at three different velocities. That means the distance that you have traveled is 330, that's the total, and the time taken is 3, right? So that's the that's the displacement that you had, and you can say it's 110, which is the average velocity of your motion, right? So each of these points, points in the velocity time graph will represent a the displacement that you had. So each of these point will represent the displacement you had in some discrete time. So the area under this curve, right, this area will represent the total displacement of the motion. Your motion, the total displacement that you had will be can be calculated by calculating the area under this curve. So that's as simple as that. Now if you look at the varying uh, we have found out that dx by dt for that curve is 6at plus 3b, right? 3b, with 6a being the slope and 3b being the starting point. Now if you remember that the change time rate, if you look at the same curve, you can find that the time rate of change of velocity, the time rate of change of velocity, which is called the acceleration. So you can say, you can do the same thing, that is acceleration is equal to v minus u, or v2 minus v1, depending upon your choice, by t or delta t. Okay, it will look like that. Now instantaneous acceleration, you can do the same thing. You can limit t to delta t tends to 0, uh, velocity of t plus delta t minus velocity of t by delta t, which will be the instantaneous acceleration. So that will be defined as dv by dt. So dv by dt can give you the acceleration of the particle. Now we have the equation of dx by dt, which is equal to v. Now we can do dv by dt, so it will be 6a. So acceleration has become a constant. Okay, so that means the plot of acceleration is a straight line. So acceleration will look something like this. Okay, it's a straight line. Now if you look at these three curves, right, if you look at the three curves, you will find that the velocity displacement time graph looked something like this, right? And the velocity, this is the displacement versus time graph. Now the velocity time graph, if I draw it in the same piece of the plot itself, so it's a velocity time graph will look like that. And the acceleration, which is the third one, acceleration versus time, that look like a constant, right? So that's how three of these graphs looks like. So that means the acceleration is not going to change, right? It will always be 6a, right? If it is moving at some velocity, it will be 6a. A can be anything, okay? A is a constant. I just randomly pick this equation. It has no meaning at all. So the velocity or acceleration will always be a constant. So for this equation, this particular equation, so you can clearly see that out of that, right? Straightforward, right? Now if you look at this equation, this set of equation, this uh, I have three equations here. Now you can see that the first equation is the actually the red curve is the position versus time, right? Position versus time graph. You can look at the positive axis if you want. You don't have to worry about the negative axis. Anyway, if you look at the positive axis, you can see that the curve is going up. The starting point is around 20, right? You started your motion around 20, and you had an acceleration, which is the velocity of the graph uh, is in the blue line. The blue line represents the velocity time graph, and the green line represents the acceleration graph. Okay, the initial starting point was 20. You started from 20, and you had a velocity. You had a velocity, the starting velocity, which was around what 8, and you had an acceleration of 6. Okay, so that's the graph, how the graph looks like, and we will come back to this graph in a couple minutes back later. Okay, now if you look at the equation of velocity, which we have written down earlier, the acceleration, which is equal to v minus u by t. Okay, that's the equation of acceleration, where v is the initial final velocity and u is the initial velocity, and t is the actual time taken for that particle to accelerate. So if that's the equation, then we can write down that v minus u must be equal to at. This is our first equation of motion, right? So this is the first equation of motion. Now if you I've already told you that the area under the curve, the if you take the velocity versus time graph, it will look like that for our equation. Now the area under the curve gives you what? Gives you the total displacement covered. Okay, that's the area under the curve will give you the total displacement. That means if you take that um, okay, like this, okay, if you like this, you can say that this is our starting point, which is u, okay, and so this distance you will start from here. Okay, I'll give a plot for you guys anyways. So if this was our velocity versus time graph, and you start from some displacement 20 meters, and you go up from there, this is the velocity versus time graph, and you can see this displacement, which is the initial velocity, which was u, right? U, and the final velocity has become v. Okay, let it be v, and the time taken for this whole thing is t. Okay, so in that case, you can find the area under this graph by using this plot itself, right? So this distance is u, and this distance will be, the top will be v, so this distance will be v minus u, and this distance is t, and this distance is t. So you can see that this area will be u times t, and the top area will be half base, which is t, times v minus u, right? So that's the top area, which is the total displacement. Okay, which is the total displacement. V minus u, as you have remember, we have did in the first equation. If you remember, you look at the first equation, you can see that v minus u is just at. Okay, so we can substitute for v minus u right there. So you get ut plus half a t times t, which is t square, which is equal to the distance. So total distance is ut plus half at square. So that's the second equation of motion. Okay, for you guys, that's the second equation of motion for you guys. Now if I get back to the first equation, you'll find that v minus u is equal to at, right? So v is equal to u plus at, and if I square that, right, you get v square must be equal to u plus at the whole square. So you can expand on that and you get u square plus 2u at plus a square t square, right? So now what you can do is just u square plus, you can take out what I'm going to take out as a common. I'm going to take out the 2a, right? So I'm going to take out 2a. The remaining will be ut plus when 2a comes out, I'll get a half here, half times 1a and half at square. So this is ut, this is v square here. So you can see that ut plus half at square is just, if you look at the previous equation, ut plus half at square is just x, right? So you get v square is equal to u square plus 2ax, right? Or you can write down v square minus u square is equal to 2ax, which is the third equation of motion. Okay, so these are the basic equations of motion, and now we have discussed about acceleration, velocity, the displacement, speed, and the equations of motion. So these are the basic things that you need to remember. So I'm going to close this whole thing right now, and I'm going to get back to that equation anyways. Now if you look at this equation, you can see that the first equation here is y is equal to 20 plus 8x plus half 6x square. This is of the form x equal to x0 plus ut plus half at square. So x0, which is the initial starting point, that is 20 meters. So you started at 20 meters and then you had the velocity which is 8 meter per second. So that's 8 meter per second. That's where you started your velocity graph. And the acceleration here is called 6 because it's the part of half at square. So acceleration is 6, and you can see that you started at 6. The acceleration graph, green graph, starts at 6. Okay, so that's the basic equation. So it satisfies the plot, and you can see the second equation, which is the velocity plot, and you can see clearly that 8 is, which is u, v is equal to u plus 8, right? U is 8 and ta is 6. So that's also clear. Or all I did was to take the first equation and then took the derivative with respect to x, and I got the velocity equation, and then again I took the derivative again and I got the acceleration. So that's what I did, and I plotted all these things right down for you guys to understand the implication of these equations of motion. So with that, I am going to close this lecture. I hope you understood all the basics regarding one-dimensional motion, and we will discuss some more things in the next lecture. So thank you guys for watching. Okay, all the best.